Hello, in this video, I'm going to explain prime factorization. All right, so problem number one here, it says identify the number as prime, composite, or neither. Now we did this a little bit in the last section, M1.7, I believe it was, the last video. So this is a continuation of that concept. All right, so we have 125. Now, one thing we can do is to look to see if 125 is on this table of prime numbers. It's not only because this cuts off at 100 or so, 97. So we got to find a different strategy to determine if this is prime, composite, or neither. So basically, we have to ask the question, can 125 be broken down into factors other than 1 and 125. And here is where the divisibility rules come into play. They're really helpful, and here's another example of where knowing the divisibility rules is going to make things easy. So we have 125. Now, we could look at the number 2 in using divisibility rules and ask if 2 goes into this. Well, this is an odd number, so 2 will not go into it. We could look at the number 3 by adding the digits, right? Recall that. To see if a number is divisible by 3, you sum the digits. 1 plus 2 is 3, 3 plus 5 is 8, and 3 does not divide into 8. Being that this is an odd number, all even numbers will not divide into it. We can skip 4. How about the number 5? Yeah, see, this ends in 5. So if a number ends in 5 or 0, we know 5 goes into it. So this can break down into 5 times what equals 125. Well, 4 quarters will give us $1. 1 more quarter, 5 quarters will give us $1.25. So remember, you can use the money analogy to help you with some of these larger numbers. Sorry, so that should be 25, right? That should be 25, right there. 5 times 25 is 125. So the fact that we could break this number down into other numbers besides 1 times 125 tells us that this has to be a composite number. Okay, it has to be a composite number. So let's try composite, because there are other factors besides 1 times 125. And here it is right here. 5 times 25 is 125. Now, they're asking for something that's called prime factorization. So this is going to be something that you'll be doing quite a bit of in this course and also in Math 50. There are various ways to determine prime factorization. And one of the easiest ways is to use what's called the factor tree. You might have used it before. You might have looked at it or seen it before. And here generally is how it works. Let's do a simple problem first, and we'll come back to this 125. Let's use 12 and pretend the instructions say use the factor tree to find the prime factorization, or to just find the prime factorization, and you decided to use the factor tree. So we got to determine the factors of 12, but not 1 times 12, because it does not help us, right? We need other factors besides 1 times 12. Well, we got a couple of choices. We can go with 6 times 2 or 4 times 3. It doesn't matter, actually. You're going to get the same answer as a result. So first, let's try 6 times 2. So these little things here are branches of a tree. That's what these represent, branches of a tree. And you're going to keep breaking down a number. This is a composite number because it can be broken down into other factors. So any composite number that remains on a branch tree, you want to keep breaking it down. But any prime number that cannot break down anymore, you circle it, because we're done with that tree. It's finished with that branch. That branch is finished. Okay? So let's look at the number 6. What times what is 6? And we know that 2 times 3 is 6. 2 is a prime number because that cannot break down anymore. And 3 is also a prime number. There it is. So once you reach to the point where all you have are just circled numbers which represent prime numbers, then you're done doing prime factorization. Now, the way you would want to write this out and type it in the computer would be this way. You can start with the lowest numbers, which are 2 2s. So you got 2 dot, which means multiplication, right? 2 dot 3. So we have 2 2s, here they are, and a 3 with a multiplication dot in between all of these, because factorization implies that you're multiplying numbers together. These are factors of 12. In fact, if you were to multiply these out, you better get 12 back, and we do, because 4 times 3 is 12. So that's how you perform prime factorization using a factor tree. Now, let's try something else since we're on that topic here. Let's pretend we didn't want to use 6 and 2, but we want to use 4 and 3. We still get the same thing? Well, let's find out. Now, 3 is a prime number we cannot break down, so we can circle it. 4 is composite because it can be broken down into 2 times 2, and 2's are prime. And look, it's the exact same thing. So the nice thing about the factor tree is that it does not matter which numbers you choose for the branches, you'll wind up with the same prime numbers at the very end. All right, so that's the concept of using the factor tree. So let's go back to our original problem and see if we can figure it out. So we have 125. What times what is 125? So, and by the way, this little point here, this is a branch. It does not point to the 2. Okay, so some people have made that mistake. No, this is just simply a branch that's coming off this base. This is the base of a tree. These are branches coming out of it. I'm not pointing to the 2, just so you know. So this number ends in 5, so guess what? I know 5 goes into it for sure. It's divisible by 5. 125 is divisible by 5 because it ends in 5. So I know that 5 times something is 125. I also know that 5 is a prime number. I'm going to circle it. Now, the work we did earlier, we know that 5 times 25 is 125. So now we got to ask ourselves, is this a prime number or a composite number? And the fact that this ends in 5 tells us that, again, 5 goes into it. In fact, 5 times 5 is 25, right? Now, we got to the point where each branch of the tree is finished because it has a prime number at the very end. Therefore, we're done with prime factorization. So you would type in the computer 5.5.5 because 5 times 5 times 5 is 125. So we got 5, and then here's the multiplication dot right here. Don't use the decimal dot. So this is in prime factorization format. All right, so here we go. Let's see if we can go a little bit swifter this time. Now, that's a huge number. You're not going to see that big of a number in math 50, But for some reason in Math 25, they gave you huge numbers. Congratulations. All right, so this is going to be a biggie, right? But remember, as we go down the tree, the number is going to get smaller. 1155. What times what is 1155? I have no idea. However, this ends in 5, so I know for sure that 5 times something is 1155. So I circled the 5 because it's a prime number. Now, how do I know what 5 times this is to give me 1155? We're going to do the opposite, the inverse of multiplication, which is division. We're going to divide 5 into 1155 to give us this. So quick and dirty, nothing fancy here. So this should be a review for you, all right? $231. 5 times 231 is 1155. All right. So as you can see, we went from 1155 down to 231. So significant drop off. We dropped off by a factor of 5. Okay. Now the question is this a composite number or a prime number? What times what is 231? I have no idea. But I'm going to use the divisibility rules to help me. So let's start with 2. Now, this ends in 1, which makes it an odd number, so 2 will not divide into 231. Let's try the divisibility rule for 3, which means add the digits. 2 plus 3 is 5, 5 plus 1 is 6, and 3 goes into 6. Oh, good. Goody. 3, which is prime, times something is 231. Again, I'm going to divide 3 into 231 to find out what this number is. Quick and dirty, nothing fancy. Oh, 3 times 77 is 231. All of a sudden, this is manageable. It's not too bad, right? Now, is this a prime number or a composite number? Well, this number here is on the multiplication tables, and by now, you've mastered them, right? Correct. 7 times 11 is 77. 7 is a prime number. 11 is a prime number, and you've also mastered these, right? All the way up to about 50-ish or so, 40-ish. All right, so there it is. So let's start with the smallest number. 3 times 5 times 7 times 11 is the prime factorization of 1155. So first, let's answer the question. Yes, it's composite because we can break it down. See that? We got other factors besides 1 times 1155. What is the prime factorization? Three dot 5 dot 7 dot 11. That's what it is. Oh, this seems relatively easy. All right, 84. 84. Now, you can pick any number you want as long as it's not 1 times 84. If you notice that this is an even number And I know 2 goes into an even number. So if you say 2 times something, it's not like you're wasting your time. It's like, oh, I could have picked a bigger number. It doesn't matter, because in the end, it's going to be this. You're going to have to pick 2. 2 is going to be part of that factorization, guaranteed. In fact, there could be more 2's. So 2 times what is 84? Well, let's think about it. Let's cut 84 in half. Let's divide 84 by 2. So 84 cut in half is what? 42. Good. Now, what times what is 42? Again, you can pick 6 times 7. You can pick 2 times 21. It doesn't matter. You still get the same number. Let's try 6 times 7 just for fun. 7 is a prime number. Here we got 2 times 3. Done. So 2.2.3.7. There's our answer. It's definitely composite. And the factorization is 2.2.3.7. And we got another one. $147. Now this might look familiar because we tackled this number in the last video, I believe it was, in a recent video. So is this a prime number or a composite? It's odd. It doesn't mean it's prime though. So this is an odd number, so we're not going to try any even number. We know no even number divides into an odd number. Okay, so we're going to skip the evens. So let's go to the next number, prime number, or number for divisibility, and that's the number 3. So let's add these. 1 and 4 is 5. 5 and 7 is 12. Aha. So 3 times something is 147 because of the divisibility rule, right? 12 is divisible by 3, so 3 goes into 147. Now, quick and dirty, nothing fancy. Aha, 49. 3 times 49 is 147. And using your multiplication table knowledge, you know that 7 times 7 is 49. So we have a composite number, and the prime factorization is 3.7.7. Well, here's a nice big one here. All of a sudden, they throw this big number at us. Lucky for us, we know our divisibility rules, right? Correct. So, 567. What times what is 567? Not a clue. Odd number, all even numbers do not go into it. So let's try the number 3 by adding the digits to get the sum of the digits. 5 plus 6 is 11. 11 plus 7 is 18. And 3 divides into 18 evenly with no remainder. Aha. 3 times something is 567. 3 is in a 5 once. 3 is in a 26. 3 is in a 27. 189. Nice. All right. So now is 189 composite or prime? Let's try divisibility rules again. 1 plus 8 is 9. 9 and 9 is 18. Yeah, 3 goes into it again. Nice. Very good. So 3 into 189. 3 goes into 18 6 times. 3 goes into 9 3 times. Very good. 3 times 63 is 189. Is 63 prime or composite? And you said composite because a bunch of different ways could be gotten here, but 7 times 9 from the multiplication table we know is 63. And then 9 is the same as 3 times 3. So we have 4 3s and a 7. There it is. So the prime factorization of a number is the DNA of the number. Every number has a distinct DNA, a different prime factorization. Pretty cool, right? Anyway, so we have a bunch of 3s here. All right. So we're still going to find the prime factorization, but the only difference here is that they want us to use exponential form for repeated factors. So for example, let's take a look at this one here. We could write this out as 3 to the 4th times 7. These are equivalent expressions. Remember, this is the base, that's the exponent, and the exponent tells us how many times the base repeats or multiplies by itself. We have 4 copies of 3, the base, and that's what this is saying, 4 copies of 3, the base. So after we do this problem, they want the answer in this format, exponential format. That's the only thing that's different about this problem. All right, so let's erase this and try the next one. All right, so what do we got here? 126, not too bad, right? Even number, guaranteed 2 divides into it. Two goes into 12 6 times, 2 goes into 6 3 times. Nice. Quick and dirty. 63 you said is 7 times 9, correct? 3 times 3. So let's write this out in exponential format. So let's start with the lowest number, 2 dot, we have 2 3s, so 3 to the 2nd power dot 7. So let's see which one matches. Is it A? Nope. Is it B? B looks like the winner, right? Looks like we got B. Well, here's a real easy one. I think you know the answer already, right? So we got 9, 3, 3 primes. They want the answers with exponents for repeated factors, and we have a repeated factor because we have 2 3s, so we have 3 squared, or 3 to the 2nd power. We have 2 copies of 3. So you type in the base 3, and then you type in this exponent symbol down here, the superscript, click it, and then you'll be able to type in the 2. All right, so more practice. Find the prime factorization of 52. Use exponents for repeated factors. Let's bang this out. So let's see, 50, right? 25 times 2 is 50, which means that 2 times 26 is 52, right? Yeah. Half of a deck of cards is 26. What times what is 26? And you said 2 times 13, correct? 2 is prime. Is 13 prime? Yes, you said, correct. So we have two twos times 13. And then you can, once your cursor's in the exponent here, just simply right arrow to bring it back down. And then you can type in the dot 13. Now here they don't tell us anything about using exponential form, so we have to assume they just want the dot version all the way through, the prime factored form without any exponents. 225. This 5 is staring right at me. I know for a fact 5 times something is 225. I just don't know what that is. I'm about to find out. Quick and dirty. Nothing fancy. 5 times 45 is 225. And then you said that, oh yeah, 45, that's the same thing as 9 times 5. Correct. Circle your primes. Our final answer in factored form, 3.3.5.5. They don't specify exponential form, so we have to assume that's what they want. Let's try it, see what happens. Nice big number. Find the prime factorization. Doing this now in Math 25 is going to really help out in Math 50. You'll see. It's well worth the effort. So there's a bunch of different ways we can break this down. To me, one of the most intuitive ways is to say, you know what? I know that 5 times 100 is 500. Boom. Now, again, we have multiple ways to do this. And again, one easy way is to say, I know 10 times 10 is 100. These are both composite. And I know that 2 times 5 is 10. I know that 2 times 5 is 10. And we're done. See that? In about 10, 15 seconds, we broke this down. And you followed right along. So we have 2 2s, 3 5s. All right, so let's put that in there and see if it works.